So what we need to do next is notice that our object IDs, our data is pretty much indexed by its object ID, and that doesn't look too convenient. So what we're going to do is agdata equals agdata.reset_index, and let's see what that looks like now. Cool, so we reset the index so that it numbers by 0, 1, 2, 3, 4 instead of 615, 713, 730. So that's a lot nicer. And then we'll create a new code block. And what we're going to do now is we're going to combine our aggregated data with the training metadata. The way we do that is as follows. All data, so all of our data is aggregate data merged with, okay, so there's a couple of inputs that we could put in here. So on the right side, we'll have the training metadata. What do I call it? Trained metadata, I believe. And then how we want it on the outer, just comma. And then on object ID. What this means is we're gonna match the aggregated data with the metadata based on their object ID, which makes sense. You want the object IDs to match up for both of those data sets. I think that's it. Yeah, so let's do all data dot head. Nice, we have all of our data now. We compiled everything into one set that we could work with. So you'll see that we have target, the Milky Way extinction, dist mod, the distance to that object, and that's in the metadata. And then we also have the aggregated data, all combined into one. Now, one thing you'll notice is passband information is kind of lost in here. Remember that the whole point of using different passbands is so that we could focus in on different wavelengths and hopefully see different things. But then by compiling the data, the passband information or the strength of having multiple passbands kind of gets lost in here. That's a little caveat from the way that we built this model, but regardless, I think this will still be valuable. There's still a lot of things that we'll be able to accomplish with this model. What we need to do next is format the target, the classes, the output that we're expecting the model to achieve. We need to format that in order for our model to be able to understand it. So let's extract our target values. So all data, we'll get the target, and we'll get all of the unique classes. So sorted y.unique. And just so you know what this looks like, it gives us all of the unique classes that we have in this data set. So if you go at the end here, this is basically what the object is. So I'll leave that as print unique classes. Now, this next part is going to be a little weird, but I'll get to it in a second. We're going to create a dictionary because we're going to map our class values so that it's numbered from 0 to 14, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, oh, maybe 0 to 13. Anyways, we want it to number from 0 to 13 or 14, not like these random values, 6, 15, 16, 42, because that's going to be a little harder to process. So for I, val, in enumerate classes, enumerate numbers the values that we have in classes. So it's going to say 0, 6, 115, 216, 342, 452, and so on. And it's a map, so when we see the number 6, we want it to map to 0. When we see the number 15, we want it to map to 1. And to create that map, we're going to say set the value equal to, so we're going to set 6 equal to I. So the way this iterates is this will be 0, 1, 2, 3, 4. Val will be 6, 15, 16, 42. So it's going to map all of those values the way that we want it to. So just for a little understanding, 6, 15, 16, 42 becomes 0, 1, 2, 3. It's nice to have things in order, you know. Now we're going to map all of our y values. And the way we do that is np.array class map val for val in y. So for all of our target values, remember we assigned our y values, our output. And for each of those values, we're going to map it to the 0, 1, 2, 3 format. And now what we're going to do is we're going to categorize these values. So y categorical. And the reason we want to categorize them is because we're working with a loss function called cross entropy. And don't worry, I'll talk about it when we're talking about neural networks. I think that's the next video. But that loss function prefers that the data be inputted as an array of zeros and ones. So to do that, we're going to say to categorical y map 14. And this to categorical we need to define. So we'll define that up here. To categorical y num classes. You'll see why these are inputs in a second. And we're gonna one hot encode our values. Now to do this, we're gonna say return np.I. So this is gonna be weird, just bear with me for a second and I'll explain it. Equals type dtype uint8. This is just a data type. It's a pretty standard thing. Believe that's how it should be. Yeah, so this is correct. So this is what you have to imagine. I is a identity matrix. This is a matrix where only the diagonals are ones and everything else is zeros. It's a square matrix. So imagine this, imagine a matrix. And let's say our class value is 2. Then we want to extract the array where the second index, or the 2th index, because it's 0, 1, 2, so 2 is actually the 3rd index. But anyways, so imagine your class target is 2, and you want to extract the correct array for that. Then when you're accessing the matrix, you only need to get that index array. And that's what this code is doing. And we're going to do that for every single y value that we've mapped. And just to get a sense of what the size of this data is going to be, we'll do y.categorical shape. And now let's run this. So we have 7,848 data samples. We have 14 classes. And also what I want to do is show you what y categorical looks like. What do our target values look like now? We're going to choose the first 5 target samples and let's see what that looks like. So that's exactly what we wanted. We wanted arrays of zeros and ones. Now we just have one final step processing this data. We're going to say final touches. The first thing we want to do is remove unnecessary data. I don't even know if I spelled unnecessary correctly. Anyways, let's think about what variables would be important to figuring out what something is. So we have object ID. It doesn't matter what the code of the object is to find out what it is. Like, no one's going to find out what kind of person you are or who you are based on your social security number. That doesn't tell us anything about who you are. So we don't need the object ID. We also don't need, actually we could just do this. This is a little weird. It might make intuitive sense for some people, but let me finish this in a second. And then we'll get back to why this is a weird thing to delete, or might not be a weird thing to delete. Gal B. So what we're deleting here are the distance and their position and coordinates. The reason we're deleting these values is because, first off, we want to simplify the model, but also I wouldn't expect location to play a huge role in revealing what an object is. I could be wrong. Maybe there's some research saying that supernova occur in one part of a galaxy more than another, or maybe exoplanets are found on the left side of a galaxy more than the right side. But this is something I wouldn't expect. I could be wrong. The universe is a fascinating thing, but as far as simplifying the model, I think these are variables worth taking out for now, at least. If you play around with it and include these values later, feel free to do so. And next, we need to remove invalid or empty data. So remember, experiments almost never go as perfectly as we'd like it to. We are bound to have empty data cells. So train mean. So we're gonna create a mean of the values in our training set, and that's what we're gonna fill the empty cells with. Sometimes you could fill it with an outlier. So maybe instead of using mean, you could fill it in with negative, some large number. And this is something people in data science play around with every now and then. So feel free to play around with that as well, see how that affects your model. But we're gonna use the mean to fill in our empty data. And then we're gonna say all data dot fill NA with the mean values in place. So in place is true. And now we need to format the data for PyTorch, or just for learning in general. So one thing that's good to do is to normalize your data, put everything on the same scale. That really helps with learning. So in order to do that, we actually need to import another library using sklearn. So from sklearn, pre-processing, import standard scaler. And this is the scaling function that we're gonna use. I don't know if we'll need to pip install this. It might already be installed, like NumPy and Matplotlib and all that, but hopefully not. We'll see. It'll give us an error if it's not installed already. So we're gonna say SS is standard scaler, and then we're gonna do my data. We're gonna scale it, so we're gonna fit and transform our data to fit the standard scaler. And then we're gonna print my data, or no, we're gonna print data shape my data.shape. And then what we're also gonna want to do is, just so we could get a sense of what the scaling did, we're gonna say my data, we're gonna get the first 5, and we're gonna do all data, what it originally looked like, and get the first 5 arrays here. And let's run this. Okay, so it looks like we have everything. If you look at the all data and compare it to the scaled data, they're on completely different scales. So that's good. We'll see how that affects learning in a future video. But with that said, that's the video. We finally got into the data. we learned how to process everything, and we have our inputs, we have our outputs. In the next video, we'll start to go over neural networks, how to make them, why they work, everything about it. So with that said, I hope you enjoyed this video, and I hope to see you in the next one. Peace.